Last time we introduced the different failure criteria based on the fluctuating stress, right? For example, like the Gutmann, the Monroe, and Gerber, and SME ellipse, and so on, right? And each criteria corresponding to each the fluctuating stress curve, okay, by experimental data, okay, by experimental data. Okay, so for this safety factor, from the different failure criteria, for example, for the Gerber's criteria, and the safety factor evaluated by the Gerber's criteria equals to the say the inverse of this formula. Okay, the inverse of this formula. Okay, therefore we can get the safety factor evaluated from the Gerber criteria equals to half times the SUT over the mean stress the square times the alternating stress divided by the endurance limit times the -1 plus the square root of the 1 plus this term square. Okay, so the same thing that we can define the safety vector evaluated by the SME elliptic. Okay, okay, so this safety vector, which is evaluated by the SME elliptic, okay, and also the safety vector evaluated by the SWT criteria or workers criteria, okay, equals to the endurance limit divided by the square root of the alternating stress times the mean stress plus the alternating stress. Okay, and here's the spatial case with the gamma equals to 0.5, 1/2. Okay, so it's the square root. Generally, this gamma vector, this parameter, has to be defined by experiment. Okay, have to be defined by experiment. Okay, so just one example for this failure criteria. Okay, so this is the piano, right? So you must familiar with if anyone you are a pianist, right? So we can just plot it's the free body diagram. Okay, you can plot the free body diagram. Okay, so suppose this point load is the 40 pound. Okay, and this must be a reaction force, right? And it will move, right? It will move. It will move. And the radius of the this groove is about the 1/32 inch. Okay, and the thickness is the 1/4 inch. Okay, so if you are a pianist, you're gonna practice every day, maybe 4 hours per day and 7 days per week. I don't know. So the question is that what is the fatigue factor, the fatigue vector of safety for the infinite life? That's mean you can practice or play the piano forever. Okay, forever. Okay, so if this component made of the steel, whose ultimate tensile stress equals to 77.5 KSI, okay, 5.5 KSI, and the SE prime is approximately about 0.5 times 77.5. Okay, and the SE, that's the practical case of fatigue loading with the marine vector. The marine vector. Okay, so suppose the surface of it is polished, therefore the Ka equals to 1, and the Kb equals to 0.969, because the cross section of it is the rectangular, therefore the equilibrium diameter equals to 0.808 times the square root of the BH, right? So it's 1 times quarter inch. So we got an equilibrium diameter is 0.404 inch. Okay, and the KB vector equals to the 0.879 times the power of the minus 0.107, right? And then we can get the KB vector. Okay, and for the KC, which is subjected to the pure bending, right? So therefore, the KC vector equals to 1. Okay, and the KD and KE, that is no, KD is the temperature vector, and KE is the reliability vector. Okay, and which are assumed to be 1. Okay, to be 1. Okay. Okay. Okay, so in this case, the F parameters doesn't have to be taken into account. Okay. Okay. So for the fluctuating stress, the two key stresses that we have to find is the alternating stress and the mean stress, right? And the KF, the stress, the fatigue stress concentration vector, and the notch sensitivity Q. The maximum stress equals to the KF times the my, the moment, times the y over the moment of inertia, right? Okay, and so here's the okay. So finally, we got the maximum stress equals to Kf times 6 times the moment over BH squared. Okay, and similarly, we can check the chart, right, to find the figure, as what the question we are asking, right? Okay, so suppose it is under the bending, right? Pure bending, right? From the geometry, we can find those dimension vector. Okay, so the W over D, W is the width, right? Over the D is the smaller width. Okay, the ratio is about 1.3. And R, the radius over the D, right? R, the radius over the D equals to the 0.16. Okay. And the W equals to quarter, R equals to the 1/32, KT equals to 1.7, right? 1.7, right? So we have the ratio of the W over D, right? E equals to 1.3. So for this curve, it's represent the ratio of the 1.4, and it's for 1.4, and this curve is represented with the ratio is 1.1. Therefore, the 1.3 should somewhere between it, right? Should somewhere between these two curves, right? And the ratio of the R over D equals to 0.16, right? 0.16. Therefore, we can approximately evaluate the KT stress concentration vector about 1.7, which is the stress concentration vector under static loading. Static loading. Okay. And then the D value, the smallest width, is the 1/16 inch. Okay. So right now we got the vector of the KT, right? The KT. It's 1.7. And we can check the chart to figure out what is this notch sensitivity is. Okay, so for the steel whose ultimate tensile stress is 77.5 KSI, so it should be somewhere in between, right? Here. Somewhere in between here. Okay, and then the notch radius, right, equals to 0.03125, okay, an inch. So it should be somewhere here. Therefore, we can find the roughly the Q vector equals to 0.7. Okay, so right now we have the KT and the Q, right? So what's the next? The next. So we can convert this KT to KF, right? So KF equals to 1 plus Q times KT minus 1. So you got the fatigue stress concentration vector equals to 1.49. Okay, and then we can plug the KF into here, right? So the moment equals to 3 times 40 and the BH square. So finally we get the maximum stress equals to 17.16 KSI. Okay. Okay, so in this case, the alternating stress equals to the mean stress. Okay. The alternating stress equals to the mean stress. Okay. Therefore, the sigma A equals to the 8.58 KSI. Okay. Okay, what's the safety factor? Fatigue safety factor for infinite life. Okay, so what's those parameter we already get is sigma A, sigma M, the SUT, and endurance limit. For this Goodman criteria, right? So the safety factor evaluated by the Goodman criteria, right? So it's the inverse of this formula, right? So we can plug those numbers, right? So sigma A here, sigma M here, and the endurance limit here, and the ultimate tensile stress here, right? So finally, we get the safety factor evaluated by the Goodman criteria equals to 2.95. Okay, 2.95. Okay, so similarly, we can utilize the Gerber's criteria to figure out what is the safety factor for infinite light, right? So plug all those values into this the formula of the safety factor. So we get the safety factor evaluated by Gerber criteria equals to 3.66. Okay. Okay, so if we use the Gerber's criteria, right? So which this fluctuating curve is for the Gerber's vector. This line, right? This curve presents the Gerber's criteria, right? Right? So we define the safety vector, right? This the stress condition, right? For this component right here. Okay, and this point is the intercept. Okay, the intercept between the loading line and the Gerber's curve. Okay, so just compare this the ratio between these two distance. So we get the number of vector evaluated by Gerber criteria equals to 3.66. Okay, the same thing by using the Goodman, right? So it's follow this the straight line, right? So can compare with this two distance, right? To figure out the safety vector evaluated by Goodman. Okay? Okay, so for the workers, the general version of the SWT, where the square root is replaced by the fitting per meter with gamma. So the previous slide I show you the gamma equals to the 0.5. Okay, that's the general version. No, okay. I mean, it should be the special case for the worker called no, a special case of the SWT called the worker criterion. Okay, that's mean the gamma parameter equals to 0.5. So this parameter gamma is determined by experimental for each material by testing at the multiple values of the mean stress. Okay, and the gamma essentially shifts weighting between the maximum stress and alternating stress to better fit behavior of each material. Okay, okay. So for the SWT or worker criteria failure, right? It's this equation, and we can define the safety vector evaluated by worker, right? And for the spatial case, the gamma equals to 0.5. Okay, you are equal to 0.5. And for steel, approximate relation between gamma parameter and the SUT, the ultimate tensile stress, is experimentally found to be gamma equals to the minus 0.0002 SUT plus 0.8818. Okay, that is in the SI unit. And the gamma equals to minus 0.0014 times SUT plus 0.8818, which is in the KSI unit. Okay, KSI unit. Okay, so there's some application to a pure shear case. Okay, so if the fluctuating stress is entirely shear. Okay, only the shear stress applied to it. The fluctuating diagram can be adapted with the following adjustment. We can place the normal stress sigma n and sigma a with the shear stress, the tau n and tau a. Okay, apply the load vector Kc equals to 0.59 for the entire shear stress to the endurance limit. Okay, and replace the yielding stress with the SSY, the shear yielding stress equals to 0.577 times the yielding stress. Okay, and this relation is based on the distortion energy theory, right? So if you shall still remember the few previous course, okay, and then replace the SUT with the SSU, the ultimate tensile stress being replaced with the ultimate shear stress. Okay, for the most material SSU ranges from the 60 to 80% of the ultimate tensile stress. Okay, so lacking specific information, okay, if we cannot obtain the enough spec information, okay, and you can use the conservative estimate that the SSU, the ultimate shear stress, equals to the 0.67 ultimate tensile stress. Okay, so one example, the other example, for example, there's a steel bar whose endurance limit is 40 KSI, and the unit stress is the 60 KSI, and ultimate tensile stress equals to 80 KSI, which is subjecting to the static torsional stress, 15 KSI, and the alternating bending stress equals to 25 KSI. And what is the safety factor is under these two stresses, okay, by using the Guman, Gerber, and the Monroe criteria. Okay, so we can define the mean stress, mean shear stress equals to the 50 KSI, and alternating shear stress equal to 0, right? Because it is the static torsion, static torsion. And the alternating bending is 25. Therefore, the mean stress equal to 0, and the alternating stress equals to 25 KSI. Okay, and we already know those safety vector, right, evaluated by those failure criteria, right? Okay. So what's the stress condition is? So first, it has the static torsion, static shear, right? 15 KSI, right? And with the bending, right? 25 KSI, right? The bending 25 KSI, right? Therefore, this steel bar is subjecting to it have the static twist, right? The static twisted, right? Static twisted. Okay, and also under bending, Okay, so you have the static torsional shear right here, and also it's applied the bending stress. Okay, so these two stress conditions are simultaneously applied to the steel bar. Okay. So we say when this bending stress, the mean stress, so for this bending, which is the completely reversible stress, right? So it's mean stress equal to 0. Even the mean stress equal to 0, this steel bar still is subjecting to a static torsional shear. Okay. So for this this bending with the tensile stress, similarly, this steel bar still is subjecting to the static torsional stress, shear stress. Okay. Okay, therefore we can plot this Mohr circle, okay, by using the von Mises stress to evaluate the safety factor. Okay, because in this case, this steel bar is subjecting to the two type of stress: the static torsional stress, shear stress, and the bending stress. Right. Therefore, we have to utilize the von Mises stress to replace the alternating stress and the mean stress. Okay, so for this pure static, this static torsional shear, right? If we can plot this Mohr circle, so we can figure out it's the principal stress, the three principal stress, right? Sigma 1, sigma 2, and sigma 3. Okay, right? So we can plug this principal stress into this von Mises stress. Right, sigma 1 and sigma 2 equal to 0, 2 equals to 0. Okay. Okay, so finally we got this von Mises stress equals to 26 KSI. Okay, 26 KSI. So use the von Mises stress, and we cannot simply use the torsional stress compared to the ultima tensile stress. Okay. Okay, so for this maximum von Mises stress, the maximum von Mises stress, as what I mentioned previously, this stress for the maximum stress will it was subjecting to simultaneously to the torsional shear and the bending, right? So this case, we are simultaneously subjecting to the static shear and the compression, and the static shear with the tension, right? Therefore, say at this point, and this point, and this point, and this point, and this point, this element is subjecting to the maximum stress. Okay, maximum stress. Right? And where's the minimum stress? Where's the minimum stress? That's mean the mean stress equals to 0, right? Here, here, sorry. Okay, so here, right? Here, right? The mean stress equals to 0. However, this steel bar is still subjecting to the static torsional stress, right? Torsional shear stress, right? Therefore, the minimum von Mises stress will equals to 26 KSI that we already calculated, right? The previous page. Okay. Therefore, the mean von Mises stress, the mean von Mises stress equals to 36, the maximum stress, plus the minimum stress 26 divided by 2. And the alternating von Mises stress equals to 36 minus 22 divided by 2. Okay, equal to 5 KSI. Okay, and the von Mises stress has the relation with the normal stress and the shear stress by this equation. Okay, by this equation. Okay, I will explain this later, but you just remember the von Mises stress has the relation with the normal stress and the shear stress. Okay. Okay. Oops, sorry. Sorry. Okay, so right now we find those von Mises stress value, the sigma m prime 31, the sigma a prime 5 KSI, the endurance limit 40, the yielding stress 60, the ultimate tensile stress 80 KSI, the true fracture strength equals to 130 KSI, which is approximately equals to the ultimate tensile stress plus 50 KSI, or the SUT plus the 345 megapar, the SI units. Okay, and then we can plug those number into the safety vector, right? Evaluated by the different failure criteria. So we can get the safety vector from the Goodman as 1.95. The safety vector from Gerber is 2.2. And the safety vector from Moran criteria equals to 2.75. Okay. Okay. Okay, so one thing you have to notice that you have to notice that some textbook will provide the wrong calculation of this failure criteria. Okay. Okay, so for some textbook, they will provide like the sigma m prime, sigma m prime, right, equals to the sigma m prime squared plus 3 times the sigma n squared. Okay, so in this case, we plug these numbers here. So the sigma m prime equals 26 KSI, and the sigma a prime, similarly, we can plug those values here. We got the 25 KSI. Okay, so in this case, the maximum stress equals to 26 plus 25 is 51 KSI, right? The mean momentum stress equals to 26, and the minimum stress equals to 1. The mean momentum stress equals to 1. And the 1 KSI is not correct. Even the pure shear, it is the 15 KSI. Even the pure shear, which is much higher than 1, right? So this calculation is not correct. Okay, this calculation, okay, is not correct. Okay, it's not correct. Okay, so what we have to work on it. So first we have to find the maximum von Mises stress. First step. Okay. And the second is find the minimum von Mises stress. Okay, so we cannot directly use the sigma m and the tau m. Okay, and then we find the sigma m prime and the sigma a prime. Okay, and we plug the sigma m prime and a prime into this von Mises stress formula. Okay. Okay, so previously I just mentioned that the relation of the von Mises stress with the normal stress and the shear stress, right? And this relation is very important for the shaft design. Okay, so suppose we have a given normal stress, which maybe come from the actual loading or the bending or simultaneously, and the shear stress may come from torsion and shear. Okay, so for the Mohr circle, we can find the center of the Mohr circle, right? Right. In this case, we have the normal stress, which comes from this normal stress comes from the actual loading and the bending, and the shear stress is coming from the torsion and shear, from torsion and shear. Therefore, the center equals to sigma plus 0 divided by 2. So the center of the Mohr circle equals to the sigma over 2. And the radius of the Mohr circle, right, equals the square root of the sigma over 2 squared plus the tau squared. Tau is the given shear stress. Right? So, and then we can define the principal stresses, sigma 1, the center plus the radius, sigma 2 equals to 0, and sigma 3 equals to the center minus the radius. Right? And we plus the sigma 1, 2, 3 into the von Mises stress equation. Okay, and sigma 2 equals to 0, right? Right, sigma. So finally, we can just manipulate, we can play with this math, right? So finally, we get the von Mises, okay? We got the von Mises stress for the given normal stress and the shear stress. Okay, so the moment stress equals to the square root of the normal stress squared plus 3 times the shear stress squared. Okay. Okay, so the course will be end here, and next chapter I'm gonna introduce the shaft design by using this relation of the moment stress with the given normal stress and the shear stress.